Okay, my last two have come right down to the wire, so I'm going to try to see if I make 6 a little faster by drawing the diagram first. So we've got this M1, M2, they're connected by pulley. This is vertical here, horizontal here. There's a coefficient of friction, mu sub k. This is accelerating to the right at A. There's tension in this cable. It's a regular frictionless pulley and crap. And we want to find the acceleration of M1, which we're calling A. So now here's something I'm going to do. It's a little sneaky, but the thing is, these two objects are not really interacting in any way except the cable. So my little trick here, my sneaky little trick here, is that I am going to use different coordinate systems for these two. So, whoops, there's my y. And then here, I'm going to do, oh man, this is so sneaky. I'm going to do x horizontally, I'm going to go y going down. And the advantage here is that when M1 accelerates this way with A, M2 will accelerate this way at A. Because when M1 goes to the right, M2 goes down, right? Because this section cable gets shorter, this one gets longer. So I'm putting my y going down so that A will be positive when M2 is moving the positive y direction. And A positive here means M1 is moving the positive x direction. Pretty sneaky, wouldn't you say? Alright, so let's, without further ado, let's look at forces. I'm going to do, actually, you know what, I'm going to do a free body diagram. I'm going to do M2 first because it's easier. So there's M2 times G, that's the weight of M2. The cable is going to pull up. Are there any other forces acting on M2? It's not touching anything, so there's no friction, no normal force. So that's actually it. You know, just the one cable and its weight. Okay, easy enough. Let's just go ahead and do an FBD for number 2. Okay, so there's my coordinate axes, x and y. Remember, I'm using this funky downward y, but you'll see why. Huh, get it? You'll see why. Pretty clever. Smith, you jokester. Alright, there's the tension, and there's M2G. So we're going to do a sum of forces. Which direction should we do a sum of forces in? Well, there's no forces in x, so that's kind of boring. Kind of pointless, too. So mass times acceleration y, and that's just going to be ma. So the sum of forces in the y direction. Now this is a little tricky because we have y going downward. So we have to remember positive y going downward means M2G is positive. M2G is positive minus t equals mass of number 2 times its acceleration. So remember, bigger this is, the more acceleration you get downwards. The bigger the tension is, the less acceleration you get downwards, or if it's a lot of tension, possibly even upwards acceleration, which would be negative. Okay, so what that gets us is, let's see, why don't we solve this one for, yeah, let's solve for tension, then we can plug that in later. I think that'll work. Okay, so T is going to equal M2 times G minus A. That's what happens if you bring the T over here and then the M2A over here, and then you flip the sides. So that's what we get out of our free body diagram for number 2, which I'm going to make pink because I'm feeling, I don't know, I'm feeling pinky today. Anyway, all right, so now we do the FBD for block 1. So now this one has normal coordinate systems, so we don't have to destroy our necks to picture it. So let's do an FBD for block 1. There is its weight. Actually, no, I'm going to draw them all in here just to make sure I know what's going on. So there's M1 times G. There's the normal force for block 1, which is really just, there's only one normal force, but because this one isn't touching anything. But anyway, there's the tension in the cable. Remember, pulleys, cables, tension's the same all the way along. If there's no friction in the cable, no friction in the pulleys, and it's light, small pulleys, what Mr. Rose likes to call physics pulleys and physics ropes that behave really nicely and don't give us any trouble, then we're all good. I like pulleys that don't make problems. Those are good. That's a good pulley. Good pulley. Thank you. All right. So then we have the friction force acting on block 1. Just your standard forces you'll see anytime you're pulling something or pushing something along a flat surface. You'll see the normal force. You'll see weight. You'll see whatever your force is, pushing or pulling it. In this case, the tension of the rope is what's pulling it. and the friction force. So there's your M1G there. And going up, you have N1. Going to the left, you have friction force on block 1. And going to the right, you have the tension. Well, they're all along axes, so we don't have to do anything fancy. So let's just sum of forces in the y direction. And that's going to equal m times acceleration in the y direction. But are we accelerating in the y direction? As usual, no. Anytime I got a block sliding along a surface, it ain't accelerating away from the surface, and it ain't accelerating into the surface. It's just not accelerating. So sum of forces in the y direction equals 0. There's normal force on block 1 minus mass 1 times g, weight of block 1. Normal force and the weight, in this case, are going to equal. So N1 equals M1G. Okay, let's do sum of forces in x, and that is going to be, we're going to have, well, it's going to be mass times acceleration in x. So sum of forces in x, tension minus friction force from block 1. Now our acceleration in the x direction is just this a here, is ma. Okay, well, gosh, let's see, what can we, right, we want to solve for the a. Do we want to solve for that or the tension? I'm pretty sure, yeah, we want to solve for a, that's right, I remember now. So, so we can say this is ma equals, I don't know, t minus f1. I guess we can say that. So we'll make that our baby blue shape. So our baby blue color. So we have the pink. We have like the girl equation and the boy equation. Pink and blue. I'm just using baby colors. Anyway, so we can combine these by taking this equation, the pink equation, and substitute that into the blue equation for t. And man, I don't even want to know where I would go with the girl-boy analogy here. But anyway, so I'm going to take this blue one, I'll bring it over here. So I'm going to fence off a little section here. Okay, so ma equals tension here. I'm going to plug this in. So that was actually, I was bad. Mass 1 times a. Okay? Important to keep these things distinct. ma1 equals this tension here, which is m2g minus m2a. So m2g minus m2a minus, oh crap, the friction force for 1. All right, well, we're just going to have to, roll with it and fix it in a minute. Okay, so what I want to do is I want to collect my a terms over here. So there's m1, and then this minus m2a comes over and becomes plus m2a. So we're going to have on the left side m1a plus m2a. So m1 plus m2 times a equals m2g minus the friction force on block 1. Blech. Okay, so friction force on block 1 is right there. So that's what's pulling us backwards. That's going to equal mu times the normal force for block 1. So m1 plus m2a equals m2g minus mu k times the normal force for block 1. The normal force for block 1 we found over here is m1g. So I'm going to find, hi, that's my fiance getting home. I'll have to go talk to her in a minute. But okay, so m1 plus m2a equals m2g minus mu k, and n1 is m1g. Mu k m1g. Okay, so this is actually going to work out pretty well. And then this may actually be just about the answer here. So acceleration, if we divide this through, is m2. I'm going to collect the g's. So it's going to be g. Yep. Okay, let's see. G times m2 minus mu k m1 over m1 plus m2. And I hope that's not off the screen, so I'm just going to drag this down one more notch. So I think this should be your answer. And I don't have the numbers in front of me to plug in, unfortunately, but as I recall from watching people do this, or watching people solve it, when you plug in the actual numbers, they give you answers about 6.00 meters per second squared for your acceleration, or like 5.99, 5.98, something like that. Anyway, there you go. Hope that's helpful.